All right, for the last time, good afternoon. Let's go in for the grand finale. So we started to talk about amino acids, and they are extremely, maybe among the most important molecules together with the nucleic acids, because, for us anyway, because they make our body function, and in fact, the bodies of many living organisms. So the proteins and enzymes are the ones in our body that enable all the processes to occur that occur in living systems, in our particular case, our breathing, oxygen transport, metabolism, growing cells, and the like. And these enzymes and proteins are made out of amino acids, polypeptide chains. And we briefly looked at the synthesis of amino acids, and that just involved three methods, all of which based on basic knowledge that you already have. One was the adaptation of the Hell-Volhard-Zelinsky reaction. Second one was the Gabriel synthesis, combined with malonic ester synthesis. And the third one was a new twist on the diversion of carbonyl chemistry when you add an amine, because you set up an equilibrium with the imine, and it's the imine that reacts as if a carbonyl was there, because it's in the protonated form, so you rig the system so it's under acidic conditions, and the protonated imine is more reactive than the neutral carbonyl. And after that, we looked briefly, did a tour of the structures of these polypeptides. So this is the summary slide we left on Tuesday. And so we have the so-called primary structure, which is simply the sequence of the amino acids. This is now big business. Amino acid sequencing can be automated, and so you can get a protein that you isolate, you don't know what it is, you degrade it to find out how many amino acids there are and what sort, and then you start using automation to basically establish what the sequence is. There are several methods that are in the book that you can glance over. Those of you going on into bio will get a lot of that. One method specifically, the Sanger method that's in the book, enables you for shorter peptide chains to do this chemically one amino acid at a time. So there are some reagents that attack either the carboxy end or more typically the amino end of a polypeptide chain and react selectively with the free amine. Remember, a polypeptide is still an amino acid, but now the amine is on one end and the carboxylic acid function is the other end. Everything else in between is amide. Okay? So the amino end will obviously react differently from the carboxy end, and so you can tag it, and by clever use of reagents, this tagging allows you to chop off one amino acid, and you can analyze what you get, and it can tell you what that amino acid was. And then you can go and start with the second one, okay, and start and keep on going. This can be done 30, 40 times or the like, depending on how efficient it is. All of these steps have to be way better than 99%, because as you can imagine, and indeed it's limited to 30, 40 steps, because in the end you are caught by the fact that it's not completely 100%. Imagine the first step is 99.5%, so you chop off 99.5% of this ball here, but 0.5% are still there. So for the second step, you have 0.5% impurity in your starting material. So that's okay, you can deal with that. So you can chop off the second one, also 99.5%. So for the third step, you now have 0.5% of the original monochop, plus 0.5% of the dichop, plus what you want to chop next. And you see where I'm going. As you keep on going, there's a buildup of the impurity, and at a certain stage, the results become meaningless. But this has been well worked out. And in fact, it's been to a great extent superseded, as we'll see towards the end today, by DNA analysis, genome analysis, where the sequence of DNA bases codes for certain amino acids in a polypeptide chain, and therefore the sequence in the DNA tells you what the sequence of the amino acids in the peptide is. So you actually now just go straight to the source of all genetic information, and from that you deduce what the structures of the proteins are. So anyway, be that as may, primary structure is just the sequence, and then these guys can arrange in slightly more complicated arrays that are called secondary, where there are two extremes. One is the so-called pleated sheet structure, where two of these chains get together and bind to each other by hydrogen bonding. And so they make like a two-dimensional sheet, if you wish, or two-strand sheet. And because of the kinks in the stereocenter, which are all the same, it's all two S amino acids, you get a symmetrical kinking that's called pleated sheet, so they look like this. Or you can get intramolecular hydrogen bonding, which gives you alpha and alpha helix of this polypeptide array. From here, you can go to a more complex array. That is, these guys can now start winding with maintaining their individual structure, either helix or pleated sheet, and can now start curving around, because these things are long enough to do this, and that gives rise to tertiary structures. And so you get arrays like this, a big sausage curling around, and you can see in this abstract rendition that the individual either pleated sheets or helix arrangements are still maintained, okay? And in fact, they can alternate depending on what kind of polypeptide you have. And then finally, you can go from tertiary to an even larger aggregate called quaternary, where several of these get together and link to each other, typically enabled by hydrogen bonding or electrostatic attraction. Could be a carboxylate that's next to an ammonium or something, so it's Coulomb's law. Or also hydrophobic type of interactions or hydrophilic, where either very polar groups, like you get close to other polar groups on the other side, or non-polar next to non-polar, that kind of stuff. So in the artistic rendition here, it's two of these. The top one, you can see the top one here is reflected in this structure, and you take this structure and rotate it 180 degrees and invert it, you get this piece here. So the two fit on top of each other reasonably well. And structures like this, we saw an example in hemoglobin that blocked the oxygen transporter. But there are many, many arrays like this. In hemoglobin, you have four of these sausages that are getting together. So that's what these look like. And so obviously knowing about the structure is important, but even more important is to make these guys. And this is also big business where there's relatively little chemistry. Because, in fact, one might say, as a pure chemist, it's boring, because you're just making one bond, and that's the amide bond. In this business, because it's actually always the same transformation, except different substrates, because you're using 20 or more amino acids, is automated. Okay, so you can buy for $20,000 or so an amino acid synthesizer, and it's got the containers which you can fill with as many amino acids as you want. If you want to stick to the 20 important ones in nature, in our body, you just have 20, and you give it to that, and then it's all automated, so you can dial in the sequence that you want. say, alanine first, glycine next, tryptophan, asparagine, and so forth, and then you go home and you come back the next day and there's your polypeptide. And this can be done now. I don't know what the current limit is, but into certainly 30, 40 amino acids in a row, maybe higher, can be done routinely. And beyond that, there are outfits that will do it for you for a price. But the essence of this stitching of this chemistry is embedded here. So this is the only section that will be something that will show up in the exam, namely synthesis of polypeptides. In fact, more specifically, a dipeptide, okay? Because the principles can be illustrated with a dipeptide synthesis. From then on, it's just repetition of the of all these procedures. And so you can generate a problem where you ask the question, what if I want to couple this selectively with this to do it in such a way that the carboxy end of this guy, that happens to be glycine, remember that's the simplest amino acid, no substituent, no stereocenter, it's achiral. Aminoacetic acid. You want to couple the carboxy end of glycine with the amino end of alanine, as this is called. That's the one with the methyl group now. Abbreviated glycyl alanine or gly-ala. Okay? So in order to do this with just the starting materials per se, you could say, I know how to do this simply. I just beat the living daylight out of the system because I know that carboxylic acids react with amines if you beat on them 200, 300 degrees. And under these conditions, the amine function will do addition elimination, do the carboxylic acid function, even with the hydroxy here, kick out the hydroxy, make the amide. And that's all fine and dandy, particularly with these two, since these are rock-stable starting materials, except you are in serious trouble with selectivity. And this is sort of schematized here. If you take glycine and alanine and you want to make selectively glycyl alanine, remember, or maybe you don't remember, but the convention is that the guy on the left is the amino end and the guy on the right has the carboxy end. So this means that we want to couple these two units here. Some of that will be formed, but all other possibilities will arise. For example, glycine will react with itself and make glycyl glycine, okay, where the carboxy end of one glycine molecule will attack the amino end of a second one. ALA will react with itself, right, and you get ALA-ALA. And not only that, all of these products, and for just the dipeptide, the carboxy end of alanine will react with the amino end of glycine to make the isomer of the desired product, namely ALA-gly rather than gly-ALA. Okay? And it doesn't just stop there because the ends are unprotected. The amino end of alaglycyl, amine on the left, and carboxy at the right, will react with more of the two components here or any of the other components. So you get polymerization, and it's a polymerization that's totally random. Okay? Because the reactivity of these groups at the two ends are pretty much the same. So the solution to that is protection. Protecting group strategy so that you block off the reactivity of the functions that you don't want to react. So this translates in the case of glycine, or making glycyl alanine, that you need to protect the amino end of glycine, and you need to protect the carboxy end of alanine. And then all that's left is that carboxylic acid and that amine, and then you can couple them. Okay? And we shall see that for that coupling, peptide chemists have invented a special reagent. In principle, you could do it by just turning the carboxylic acid into the acid chloride, for example, and then do nucleophilic addition elimination. It's perfectly fine. Okay? But it makes HCl. The yields are not 100%. There's a reagent, several reagents actually, but one particularly popular that will do this in near quantitative yield. So we'll do the next 10 minutes or so protection. Fortunately, these protecting groups, even though they look at first sight a little weird, are actually based on chemistry that you know also. So there's nothing fundamental that is occurring here. The first one that I'll look at is an amino end protection that uses a benzyl oxycarbonyl as the protecting function. And you can probably, now that we've done this for a while, you recognize an interesting feature here, namely the benzyl oxy bond. Whoops. Doesn't want to come on. Oh, it's giving up. And the benzyl oxy bond, remember, is labile under catalytic hydrogenation conditions. You can cleave this bond, and this is, in fact, the deprotection step. So what we need in order to put this on, we need a reagent. Okay, so that's a reagent you need to remember, but remember that it's based on the benzyl oxy function, and then you just tag on an oxycarbonyl. So strictly speaking, if you were to hydrolyze this, you would get OH here and OH here. That's carbonic acid. So it's a carbonic acid derivative, okay, where on the left we have an ester type function, on the right we have an acyl chloride. That acyl chloride is the one that we use to make the amide bond. And it's a special acyl chloride. It's not as reactive as a normal acyl chloride because this oxygen donates into the carbonyl, making the carbonyl less reactive, okay, like the typical electron pair resonance. Okay? So it's a slightly modified, attenuated in reactivity type acid chloride. And it'll react under mild conditions. You mop up the HCl that you get with some base, typically sodium hydroxide dilute, and out comes the amide. Okay? And so that means you now have glycine protected at the amino end, and you can go to town and do whatever you like with the carboxylic acid function. In peptide chemistry, you make a peptide bond to another peptide. The deprotection step, and I'm just doing it on the stuff that we just protected, involves the benzyl oxy function. Here what we do is we do catalytic hydrogenolysis. The usual conditions, hydrogen, palladium, and carbon. If you don't remember carbon, it's palladium, that's the essence. And it cleaves this bond to make methylbenzene, or toluene as it's called, common name, and it makes this weird carboxylic acid, which actually turns out is called a carbamic acid because it's a carboxylic acid on the left and an amide to the right. So if we go back to the analogy of carbonic acid, it's a carbonic acid where the left thing is intact, but the right is an amide. Okay? And these are called carbamic acids. And these are unstable, just like all of these derivatives are unstable, related to carbonic acid. Remember, carbonic acid is CO2 plus water. Okay? So carbonic acid is in equilibrium in your soda pop. As you drink it, you drink a little bit of carbonic acid. Most of it is carbon dioxide, but there's an equilibrium between the two. So derivatives are also unstable and kick out carbon dioxide. Or I may remind you that we've seen carbamic acids previously in the Hofmann rearrangement. Okay? Hofmann rearrangement was the reaction where an amide with basic bromine turned into an amine where one of the carbons had been kicked out as carbon dioxide. And the kick-out step involves a carbamic acid also. At any rate, this just blows out CO2, and out comes your, you have your amine. And if you've done some chemistry over here, which in this chapter means we're going to do peptide coupling, but in fact this is general. Okay? This is a protected amino acid. You can make whatever you like over here on that carboxylic acid piece. Apply your carboxylic acid knowledge to it. And you liberate then the modified carboxylic acid. So that's one protecting function. And remember, we've used benzyl oxy as a protecting group for alcohols. It's the same principle. You can view, except that now we're doing it via this linkage to protect an amine. And remember, the reason that this was useful in an addendum was because deprotection occurs under neutral conditions, catalytic hydrogenation. It's also green conditions. That's one of the cleanest reactions where you use hydrogen gas and just starting material, and out comes the product. And it was invented in part because the other popular protecting group for alcohols was tertiary butoxy. And that has to be put on and taken off by mild acid. So it's mild acid because it goes through tertiary butylcation, but it's still acid. So if you want to avoid acid, benzyl oxy is the way to go. So by that token, the other protecting group is the analog of this, where instead of benzyl we have tertiary butyl. So it's the same principle, analogous to alcohol protection. We now can also use the tertiary butoxy carbonyl function. And here it is. Okay. And so as you can already predict, the way to deprotect is mild acid, because this thing will fall apart by protonation on this oxygen or that oxygen, and then T-butylcation coming off. And T-butylcation does E1 to methylpropene, 2-methylpropene, or isobutene as it's called. So it eliminates proton and you get the alkene. And that is a gas and it disappears. So there is one slight twist. One could, in principle, use tertiary butoxycarbonyl chloride. That would have been the complete analogy to this guy. Okay? Instead of benzyl, have tertiary butoxy. That's a known reagent. It's commercial. People don't like it that much because the reagent, as an acid chloride, when you use it, makes acid and HCl acid. And even though you can buffer it and add base and so forth, HCl in the presence of the T-butoxy group, you realize you're generating conditions that are potentially causing deprotection. So in order to avoid that, you use a milder version of the acid chloride, namely anhydride. And that's straight out of chapter 18 or something, where we discussed acid chlorides are the hottest carboxy derivatives. Anhydrides are much less reactive, but still quite reactive. And when you use anhydrides, we always separate the electrophilic part, so it's labeled blue here, from the leading group part. Okay? So this is now fulfilling the function of the chloride that you would have had if you had the acid chloride. Okay? So this becomes a leading group. And I randomly chose the left piece here to make that blue because this thing, of course, is symmetrical. And so this generates as a side product. This is a leaving group as the anion, which actually then loses carbon dioxide, so it's actually tertiary butanol as the side product, and that is not particularly harmful. And the tertiary butoxy carbonyl gets attached as the protecting group to the amine. So you treat that with that, you get addition elimination, adds to this, and then you eliminate this, and out comes the tertiary butoxy carbonyl protected amino and protected amino acid, now exemplified by a generic amino acid, where this is R coming towards you when the zigzag goes up. So that's S. And that goes a very, very high yield. And deprotection is then done with mild acid, because it's T-butoxy, so you deprotect by protonating, and it's typically aqueous acid or some acetic acid or trifluoroacetic acid, room temperature. And this goes by protonating here, and then by relay, electron pairs move this way and that way, and tertiary butylcation comes off, almost as if it were a proton. Okay? And that generates the intermediate carbamic acid, where this is COOH, and that loses CO2, and out comes your liberated amino acid. Okay? So there are two conditions that you can use. So much for amino protection. Fairly simple, but you have to think about these oxycarbonyl, either tertiary butyl or benzyl oxycarbonyl reagents. Now let's talk about carboxy protection. Now, carboxy protection is actually much easier. We already know the chemistry there. That's simply protected as an ester. Okay? So you just use the ester chemistry that you know to do that protection. So typically, you use methyl or ethyl esters, and what you do, you take the amino acid in alcohol solvent to use a huge excess of the alcohol that drives the equilibrium of carboxylic acid plus alcohol turning into ester plus water. That equilibrium is driven totally to the right, and out comes the corresponding ester. An alternative to using methyl or ethyl is, again, benzyl. And we've seen that briefly earlier on. If you make a benzyl ester, you can take it off by catalytic hydrogenolysis. Methyl and ethyl esters, you take off by the reverse of the initial ester formation, except now you use a huge excess of water, so that the equilibrium that was initially pushed to the right is now pushed to the left. So I'm just showing the example with benzyl. If you take an amino acid, and so for this example, I picked something a little bit more complicated. Don't get confused by the spinach that's out here. The action piece is up here. Okay? And this is just the R group. And I picked this one because to remind you that we have looked at indole before. So that's tryptophan, and that's got the indoleal substituent. But the action is here, and so you treat that with benzyl alcohol, acid catalysis, a drop of a bubble HCl fluid, or a drop of H2SO4, and you form the ester. Okay? And you deprotect the ester, which is now benzylic ester, by catalytic hydrogenolysis, which cleaves here, puts hydrogens on the two dangling ends once you cleave, and so that gives you back the carboxylic acid and methylbenzene or toluene. You may also remember that there was another way, actually, to make these things, the benzylic esters, where you take the carboxylate plus benzyl bromide. And that works particularly well for, so it's an SN2 reaction, particularly well for benzylic halides, because you may remember that benzylic positions are unusually reactive. So the SN2 on those is particularly good, and that will give you the same compound. So either way is fine to use. And that's it for protection. And so now we enter the step where we look at